So I'm going to do this brief history of the BSD Fast File System, but really I'm more interested in sort of looking at the evolution of the technology of file systems. But since I happen to have a bit of knowledge on this particular file system, I figured I could use it as a good anchor to talk about the history here. So the original Unix file system, that is the one that came out with version 6 and 7 and so on, was just a linked list of all the free blocks. And you just took off, when you needed a block, you just took the first one off the list, and when you freed things, you put it onto the list. And one of the disk manufacturers once described this as sort of the thin film effect. All the free blocks rise to the surface and spread out. And in not very much time, your layout was completely random on the disk. And so the throughput was essentially how many blocks were in the file, because everything was a long seek. So the first thing that we did was, first of all, to improve the reliability, figure out what are the critical things that you need to write so that the file system stays consistent. I mean, you'd say, but of course, every file system needs to do that. Well, I will point out that ext2 didn't do it either. And they were like a decade after this work. So it takes people a while to realize that curdling people's file system data is not a good career move. One of the things that I learned is that people were willing to tolerate flaky operating systems. They'd crash and reboot, blue screen of death several times a day. They could cope with that. What they wouldn't cope with was when you came back up, if your file system was gone and you had to go to your possibly non-existent backups to get your data back. So what would happen is that if you weren't reliable, then your file system would get this reputation that it wasn't reliable. And so things like RiserFS, which early on tended to curdle file systems, got this reputation for not being reliable. And even though within a few years it was reliable, it just had that reputation. And people just won't trust it and won't use it. The running joke is, write a bad file system, go to jail. At any rate, the first thing that we did after getting the reliability was to increase the file system block size from 512 to 1K. And it immediately doubled the performance because, as I said, the throughput was a function of how many seeks you had to do. So if you cut the seeks in half, you nearly double the performance. It also got rid of the need for indirect blocks for a lot of files because most of the files are small. But it still utilized about 4% of the disk bandwidth. Now, disks at that time were so much faster than the CPUs and the main memories that that was sort of good enough. But obviously, it's a problem that is ripe for improvement. Enter the fast file system. So the idea was we'll have a hybrid block size. You can have large blocks, and then they can be broken down into fragments. And large files use the large blocks, and small files can use as little as just a single fragment. And so the first deployed this, we used 4K blocks and 512-byte fragments, which then meant that we could still use a single sector to store the smallest of the files. And this is where the original design came in that Margot alluded to, and that is that I decided that I would break the implementation up into the policy and then the actual thing that managed the bitmaps. And that code that managed the bitmaps I wrote in 1982, and I have never changed it since. Actually, that's not true. I've twice tried to change it and it broke something, and I'm like, what was I thinking? So I just put it back. One of the side effects of this is that you can take a file system from 1982, if you can find a way to plug in the disk in or get an image of it, and it will still work today on the file system because that low-level stuff just hasn't changed. And the policy routines, that's where all the interesting stuff is, where you're constantly, the technology changes, so the way you want to do layout changes, et cetera. And the great thing there is you can write the worst policy imaginable. You could write a policy that is everything should be on sector 1 and put that in as a policy, and the underlying implementation will ensure that you never actually double allocate. Now, you're going to get something that looks approximately like the original file system in terms of layout, but the point is you can't break things by changing policies. And so you can just try any policy you want and sort of see how it works. And you never have to worry that you're going to curdle the file system. I would say that was the single best design issue that got made, and I highly recommend that if you're doing stuff with file systems. The other thing that's kind of amazing to me, at least, is that this file system is still in wide use today. Obviously, there's a lot of more forward technology, which I'll be talking about later, but in small embedded systems, this is still the file system of choice, and there's a lot of embedded systems these days. So if you had told me 30-some years ago that I was going to be standing in front of 500 people talking about the file system, I would have wondered, what ACID version you were on at the time, which there were a lot to choose from in 1982 in Berkeley. All right, so the original file system knew all about the disks. In those days, a disk driver was a piece of art. You had to know the exact geometry of the disk. When you wanted to do a transfer, you had to do two interactions with the disk controller. First, you said, I want to seek to cylinder number 482, and then you would get an interrupt saying, all right, I'm now on that cylinder, what would you like me to do now? And there was actually a rotational register that told you at what rotational position the cylinder was so that you could then initiate a transfer. You could do seeks in parallel, but you could only do one transfer at a time. So the rotational register let you figure out which one was going to come under the head sooner so that you could make that the one request that you put out rather than the other one. So you could essentially get both of them. At any rate, the file system knew all about this geometry, and so when it would be laying out blocks, it'd say, well, I can't get the one I want on this track, but if I go down 3 tracks, then the block I want is going to be available, and et cetera. Well, by 1986, the manufacturers had dropped all this disk geometry stuff, and in fact, they sort of hid it and made it very difficult to figure out what it was. And so we said, all right, we're done with that, and we just rip it out, which is another one of the things that I think is really something that a lot of software doesn't do today, and that is if you don't need something, get it out of there and just simplify what you're doing and don't carry stuff around as legacy stuff forever and ever. And so from there on out, we just said, all right, well, we don't know what the geometry is, so the best thing for us to do is just lay things out contiguously. That is, if we assume that blocks are laid out more or less together on disks, which isn't necessarily true, but it's mostly true, then if you lay things out with sequential block numbers, you're going to get a good layout. We kept the name cylinder group, but it's really just a way of talking about a collection of blocks that are being managed. So the next thing that came along in 1987 was this notion of file system stacking, which is work that I at least first learned about by David Rosenthal when he was at Sun, and then later got picked up by John Heidemann as his PhD thesis at UCLA. And that was this whole idea of we'll just carve up the different bits of the file system, and so instead of having to have one file system that does a whole bunch of stuff, we can just make these layers and sort of push them on when we need it. So at the bottom we have the very uncooperative, doesn't do anything, the E operation not supported file system. And then on top of that you could push a local file system, in this case UFS or FFS. And then you could push an NFS server on top of that, which would then export that out. And for your local administration, where all the group numbers and usernames and numbers are all the same, you can just immediately make that available. And if you're exporting to someplace else where you don't have consistent password file or group file, you can push in a UID, GID remapping layer to get from the local mapping to whatever that export one is. And so the beauty of this is that you're not paying the cost of the remapping if you don't need it, and if you do need it, you can have however complex a mapping you need. So the local folks just get straight NFS, and the others can remap as needed. We don't have the UID, GID mapping in NFS because that's just more stuff that you've got to carry around and maintain that's not really apropos to a lot of systems. And so the whole ability to just put these things in individual modules and then you have them if you need them. And the way the layering works is an operation comes into the layer. That layer can act on it and simply respond. It can just pass it through to the next lower layer, or it can make some changes and then pass it through. So the UID-GID mapping example will take the credential that comes in, change the credential, and then otherwise just pass the operation down. And similarly, when it comes back up through the layer, it flips the credential back again. All right, and if some operation gets all the way to the bottom and nobody picks it off, then you get operation not supported. And this allows you to expand the set of operations that you have without having to go into every file system and teach it about that. So let's say we add some kind of a start and end transaction. We can, we don't have to put it in all these layers. If none of them implement it, then they'll just get operation not supported. And if we have a layer in there that understands it, then they'll operate on it. By 1988, it became clear that disks were getting bigger, hard to believe. And so we decided to raise the default block size to be 8 kilobyte with 1 kilobyte fragments. We were going to waste a bit of space because the really tiny files now would be using 1K instead of 512, but it nearly doubled the throughput because you just reduced the number of things you need to do, similar to what we saw earlier. All right, so now 1990 rolls around, and we decided to do this thing called dynamic block reallocation, which is a fairly simple thing to implement and proved to be quite effective, but was not widely picked up. And I've never really quite understood why that is. I mean, it's been more or less superseded with the newer style of file systems now, but for a very long time, it was sort of the secret that made UFS, FFS work so well. So sort of lay out a little bit about it here. Once we started having disk caches and tag queuing and so on, it really became desirable to do absolute contiguous file layout. And the problem is that when someone does an open, they don't have the courtesy to tell you how big they're going to make the file. And so when that first write comes in, you have to make some kind of a decision about where are you going to put that block. And if the choices are, well, it might be a big file and I should put it over in this area that I got lots of contiguous space, or it might be a small file, in which case I should put it in one of these little fragments that I got lying around. Well, if you always assume that they're going to be big, because some of them will be, then pretty soon you don't have any big contiguous space left anymore. And if you always assume it's going to be small, then the big files end up with a really lousy layout early on because they've got all these little pieces until it's going to be big. Well, sorry about that, And it's the startup time on files before you've got read ahead going that it's most obvious that you've done a bad layout. So the question is, how do we deal with this? How do we solve this dilemma? The idea of dynamic block reallocation is to say, let's assume that everything's going to be small, and we'll lay it out. We've got this one piece that's just the size we need, we'll put it there. And then they come along and they do another write and go, well, it's not quite that small, it's a little bit bigger. But I got these two blocks over here I could use, so we just pick up that one and put it over, the first block and put it over there with the new block. And as it grows, we sort of move it around and around and around and around and around, and eventually go, oh, this is a big one. Okay, great, let's drop it at the beginning of this big contiguous area here. Now, it sounds like there's a lot of reading and writing that's going on there, but this is where the buffer cache normally saves us, because we're just building this up in the buffer cache. And so when we say we're reallocating where it goes, we're just changing a header in the buffer cache that says, well, when you finally get around to writing it, this is where it ought to go. Now, if you actually have a slowly growing file like a log file, it does actually get written in one place, and then it gets a little bit bigger, and it gets read in and then written out somewhere else. But it's a slowly growing log file, so the extra I/O is just not that noticeable. And later, when you go to grep the thing, it is, again, laid out really nicely. So, fairly simple thing to do. It really just means that you need to manage your buffer cache a little bit differently. But the effect of it is dramatic. And that is that after a file system's been in use for 2 or 3 years, the degradation of throughput is only about 15% over what you would get in an optimal layout. And most file systems by that time sort of pan out at about a 40% degradation. Now you might ask how one actually knows this, because it's sort of hard to run experiments for 3 years to find these things out. And luckily, there were these folks at Harvard, Margot Seltzer and Keith Smith, who decided that they wanted to be able to actually test these things out. And so they spent 3 years on one of their file servers collecting essentially making a trace of every allocation and free that happened. So they weren't keeping the actual data, but just keeping track of all the blocks that were allocated. This file allocated a block, that file allocated a block, et cetera. And then over about a 3-day period, they could replay that. So they could create a brand new file system and then replay this, and boom, they could see what it would look like 3 years later. And so they took this thing that I had done and they said, okay, well, let's enable the dynamic block reallocation, and boom, 3 years later, it was doing about only 15% degradation, and then turn it off, and then 3 days later, they determined that it was down to sort of 40% degradation. So it was a great paper, and I figured, well, look, this is such a huge win. Everybody's going to do this. Nope. So I continue to fail to understand sort of, how there's uptake of some things that seem sort of silly, and then other things which seem like they're huge and they just don't get done. All right, so by 1996, we pretty much had large file throughput sorted. If your file system knew what it was doing, you could pretty much get 95% of the bandwidth of the disk for your large files. So that was more or less a solved problem, and where we were starting to see problems was reading and writing lots of small files. You might notice that we're getting into the internet era here, the web era, and there's all kinds of little baby files that are, when you go to pull in a page on a web page, you got to grab all these little images and other things. And so it really started boiling down to being able to read and write small files quickly. In particular, the synchronous writing that we were doing to keep the file system consistent, you needed to do 2 synchronous writes to either create or delete a file. And the number of synchronous writes you can do on a disk is a few hundred per second, which really put a crimp in reading and writing a lot of small files quickly. So there were a number of techniques. I'm going to actually just go sort of quickly through them here for dealing with this. Soft updates is just one of them. The idea is that you want to keep the file system consistent enough that, well, in this case, you don't even need to run FSCK after a crash. And you also want to ensure that you never have unwritten data blocks showing up in files, which was common up until this era. And obviously, you want to minimize the number of synchronous disk writes that you need to do. So how do you keep the metadata consistent? There's lots of different ways you can do this. I'm not going to really drill down into all of these, but I just want to sort of catalog them because it's sort of interesting to look at all the different ways that people have found to solve this. The original way was synchronous writes. You just ordered the writes and made sure that everything was done in the right order, and then the file system was consistent. It was simple, it was effective, it was easy to figure out, but it was slow for a lot of creating and deleting of small files. So sort of the first attempts were this notion of, well, we'll have some NVRAM available to us, and we'll just put the stuff in the NVRAM that needs to be done, and after a crash, we'll just go through the NVRAM and make sure that all that stuff got done. And we actually did the hooks that you needed for that in the fast file system on the grounds that, well, soon all machines were going to have NVRAM on them because it was such an obvious thing to need. And we waited, and we waited, and we waited, and we eventually determined that perhaps not. And it's really because NVRAM is just nasty stuff. It's expensive, it's slow, it usually needs batteries. The batteries die usually about 2 months before the disk dies that you're depending on it saving. And so, yes, that is used in specialized stuff like network appliance boxes or other big things where you can essentially have some software that's monitoring the batteries, et cetera. But on the general purpose machine, it's just not there. So next option is atomic updates, either journaling or logging The journaling is where you're only tracking the metadata. Logging is where you're tracking the metadata and the contents. And so, again, you have all these writes that sort of need to be done scattered all over the disk. Instead of doing that, you just create a log, so you just in one place say this all needs to be done. So you're still doing sort of, well, actually twice as many writes, because you write it to the journal and then you eventually get it to where it needs to be. But the slowdown doesn't occur because the journal can be written, all in one place. So you get the head there and then you just go bump, 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 bump and write a whole bunch of things. So this is a technique that's widely used today. It generates some extra I/O. It doesn't really help you much if you've got a light load, but who cares what it is on a light load? It's the heavy load that you care about, and that's where it really works well. So the real technology shift has come with copy-on-write file systems. This actually started with Mendel Rosenblum on the Sprite project at Berkeley, then Margot Seltzer and others at Berkeley turned it into something that was actually usable in a production environment. And that was used, in fact, in the NetBSD as their primary file system up until fairly recently. The big issue with the original log structured file system was that you had to do garbage collection. And so the little tweak that got made to really turn it into something that became widely usable was the notion of, instead of doing garbage collecting, tracking the blocks, which is a fairly tricky thing to do, but it's possible, so that you don't have to do garbage collection. And so from LFS then, today we see the ZFS, the zettabyte file system, originally from Sun Microsystems, the Waffle file system from Network Appliance, and so on. And the copy-on-write file system has the benefit that you're never overwriting anything. It's just always writing in new stuff in new places. And so your file system is always consistent. You never have to worry about it being inconsistent because you just move from checkpoint to checkpoint. You take a checkpoint, all right, that's your consistent file system. You do some stuff, you take another checkpoint, and once the checkpoint is committed, you've now moved forward to that point. You got to do logging or journal. Well, you actually have to do logging to track what's going on in between, because taking a checkpoint is expensive enough that you can't do an fsync by doing a transaction commit or a checkpoint. So you have to do some logging for those in-between states. But as long as you don't go too long between taking checkpoints, which you typically don't, 5 or 10 seconds, the cost of recovery is just walking through there and doing those operations to get the file system back to the leading edge of where it was. So this is very popular, and especially when you get into the really huge file systems, the copy-on-write file systems just absolutely run circles around any overwriting file system. So people say, well, is ZFS going to replace the fast file system? Well, the answer is probably not. The overwriting files, or the copy-on-write file systems, need far, far more resources to work well. ZFS, first of all, you've got to have a 64-bit processor. You've got to have at least 16 gigabytes of memory, and that's assuming you're not trying to run particularly fast. 100 is better. And the reason being, you've got to cache stuff, because things are being written temporally. And so something that's written over a long period of time is just going to be spread all over the disk. And so to get any kind of reasonable read performance, you've got to be able to just bring all the things you're actively reading into memory and just have them sitting there. So for the big systems, it's unbeatable. I mean, snapshots or reliability or many other things that you really like to have in your huge file systems, they do great. But you're just not going to put that on the embedded box that's going to be your router in your house. It's just not happening. So there's still a place where the overwriting file systems have a niche and is not likely to go away in the near future. Okay, and so I talked about soft updates, which is really another way of achieving the same thing as journaling or logging, but you do it with in-memory data structures. So you're trading off using more memory to avoid the extra I/O. So you do less extra I/O with soft updates, but you use a bit more memory. And in the old days, when they were first done in the mid-90s, that was a big deal because you needed like half a gigabyte of memory to really make it work well. Half a gigabyte of memory today is like, who cares? That's nothing. The other thing that sort of the trade-off between the copy on write file systems and the traditional overwriting one is that the overwriting ones can really use the disk right up to just about the last couple percent, whereas the copy on write file systems start to really struggle if you're more than, well, the recommendation is you don't fill them more than halfway full, and you really don't want to fill them more than about 3/4 full. Again, when you got lots of disk, this is not a problem, but when you're in an embedded application with very limited disk space available, you really care. So like the latest Sony PlayStation, they had originally, well, it's built with FreeBSD. They'd originally planned to write their own specialized file system, but they couldn't get it to become stable. So like 4 months before they're going to ship it, I get a call saying, hey, we need help because we're going to have to use FFS. And by the way, we need a 10 megabyte block size, and it doesn't seem to work very well when we specify a 10 megabyte block size. But luckily, I was able to change some policy routines, and boom, it all worked. And they didn't have to worry about it staying stable because it was just policy routine changes. All right, so the next sort of big piece of tech that got dropped in was snapshots. This is something that the copy on write file systems had. It was really easy, right? I mean, you just didn't reclaim old space. You just kept one of your checkpoints and the things that hung underneath it. This is a little trickier to do when you've got a overwriting file system, because now you've got to check every single write to see if you're modifying something that's in a snapshot and make a copy of it and blah, blah, blah. So that oven by itself limits what you can do. In particular, the fast file system won't let you have more than 20 active snapshots, and it's still it's a non-trivial operation compared to an overwriting file system. So they're there, but again, if snapshots is what you need, you should be using something like ZFS or Waffle or whatever. By 2001, it seems that disks were getting bigger again, and so we changed the default block size to be 16 kilobytes with 2 kilobyte fragments. Now the smallest files are using a minimum of 4 disk sectors, because amazingly, disk sectors hadn't gotten any bigger in 30 years. We sort of kicked up the throughput, but we started wasting more space because now the small files were using a minimum of 2K. Meanwhile, the soft update stuff had done well, and as I had mentioned, it kept the file system consistent enough that you could just crash and reboot and crash and reboot and crash and reboot without ever having to run FSCK. But the problem was that it would lose data. That is, it would think that there were blocks or inodes that were in use that in fact had been freed, but the maps hadn't been updated to reflect that. And so over time, you just sort of lost space. And you got to the point where you wanted to reclaim that space. Well, FSCK runs sort of proportional to how big your file system is, because it needs to look at about 4% of all the disk space in order to make up its mind what it needs to do. And when you get sufficiently large file systems, you were looking at half an hour, a couple hours of FSCK running. And FSCK needs an absolutely static file system. So you would have 2 hours of downtime after a crash if you wanted to run FSCK. So there's never really a good time to do it. And so we came up with this idea of saying, well, we could write a real-time garbage collector that's working on a live file system, but that's hard. And I'd already written FSCK, and I really didn't want to do that again. So I decided that we would just find a way to reuse the existing FSCK. Well, it's easy. We'll just take a snapshot, and then we will run FSCK on the snapshot, because that's static. And it will come up with a set of the blocks that were lost. And they're still going to be lost no matter what else has been going on, because they're lost, and as far as the file system is concerned, they're not available. So we can take as long as we want to find them. And then all we need to do is write a special system call that allows us to, if we're privileged, to go in and say, all right, you think this block is in use, but actually it's not. And it'll, under the proper locking, flip the bits in the map and put them back to being available. Same thing for the inodes. In this way, then, you get reused 98% of FSCK, and you just have to write a little bit of extra code and have snapshots available. Yeah, so basically talked about that. All right, well, 2003 comes rolling around, and it's disks continue getting bigger. Now, back in 1982, the original file system used 24-bit block pointers. And when I was writing the fast file system, I talked to Bill Joy, who was running the project at the time, and I said, well, I'm going to increase these to 32-bit block pointers because then I don't have to do this pack and unpack stuff, and it's just easier. And he's like, oh, that's crazy. You're never going to need all those bits. And he had some argument that's based on physics about, maximum density and molecules and blah, blah, blah. Anyway, the disks were never going to need that much, but OK, he'd tolerate it. So I don't know, physics changed or something. And by 2003, we seemed to be getting disks that were bigger than was theoretically possible in 1982. And we were running out of bits. You could play some games, so you might get up to about a 4 terabyte file system, but then you were just, that was it. You were done. And so we considered, should we just rewrite a file system from scratch here, or do we want to try and just modify the existing one? Well, by this time we've already got overwriting file systems, or excuse me, copy on write file systems and other things. So it's clear that the really giant market is well served at this point. And we sort of realized that our place in the world is to deal with the smaller systems. And so we didn't really need to worry about the zettabyte size. Someone else had dealt with that problem. And we would be better off to just sort of expand so that we could handle the disks that we would be likely to see over the next few decades, but keep with the existing file system. Because in that way we could take the existing file system and just make sort of some changes to it to deal with bigger blocks, but not have to change all the rest of the code. And so the beauty of this is that we can reuse almost everything. There's a couple of macros that get dropped in that basically say, pull out this block, and it just looks to see what size the block pointer is and does the right thing there. So it meant that we could do fairly quick development and deployment. In particular, I didn't have to change the way the allocation worked. And so it became stable and reliable fairly rapidly. And the same code base supports both the 32-bit blocks and the 64-bit block file systems. And the amount of code that's specialized just for one or the other is about 5% of the file system code. And so if something breaks or some feature gets added into the code base, it just works for both sets of file systems. And it also means that we continue to be able to support the legacy file system. So those of you that are still running with your file systems from 1982 will be perfectly happy to be able to read and write them on current systems. So we put that in. We did take the opportunity, since we were making the inode bigger, to do a few other key things. In particular, the 32-bit time was an issue. It was a particular issue for me because time runs out on my 84th birthday, at least if I'm in the UK. And I'm thinking I might still be alive then, and I don't want like a search party to be out for my hide. So I bumped up the sizes to 64-bit times on the grounds that they were giving people a good 30 years or so to get switched over, and there's still going to be some nuclear power plant or something, but hopefully by that time they will have decommissioned it or something. All right. So next up is extended attributes, file forks for those of you from the Apple land. The idea is essentially some extra stuff that we keep about the file that's not actually in the file itself. Now, of course, all file systems have this, but in the traditional Unix, it's just in that small fixed size inode. So you have UID and GID and mode and things like that. But if you want sort of something that's more comprehensive than that, there's no place to put that in the inode. And the only other place is to put it somewhere in the file, and then it's in the way. So when we redid the inode for the the bigger block sizes, we also put in a couple of extra blocks to reference things that would be the extended attributes. So the idea then is that that's a place where you can put extra stuff. And by integrating those block pointers into the inode itself, we get the same guarantees of consistency through fsync that we get for the rest of the file. So when you do an fsync, you get not only the data synced, but all the extended attributes synced. And the extended attribute storage is just logically a list of things. And the header of each thing is something that tells you how big it is. So if you don't recognize what it is, you can at least find the next one on the list. And then a couple tags to identify. One tag is this something that the system is managing, or is the user managing it? And then what it is. And what it is defined by either the system or the user. So you can, as you'll see, we'll be able to do things like ACLs in there. But the user can put in little pictures if they want to have some, picture that represents what the contents of the file is, such as you would see on a typical desktop system. So the first thing that we actually used these for was access control lists. These are things that have been around for a long time, and they essentially allow you to be more specific about access to the file. So instead of just having the owner, the group, and everybody else, you can have a list of all the users, each of whom can have different access permissions, and all the different groups with their access permission. And so you can be very much more detailed about who can get access to that particular file. So the implementation of this, we'd had them earlier, but it was sort of this auxiliary file that was associated with the file system. And so when you would sync when you'd sync the file, you wouldn't be syncing that. And so they could get inconsistent. And it was sort of fixed size structures. So you could have a maximum of, I forget what it was, 10 users or groups or something, but not arbitrary size. And so by moving them out of that implementation, re-implementing them as part of the extended attributes, since the extended attributes can be 64 kilobytes in size, you can have a very long list of users and groups, and you get the atomic update of that. So it really took something that was fairly ad hoc and didn't work very well and turned it into something that worked extremely well. And luckily, this is the case because now in like NFS v4, you actually have to have that stuff work. As before, there was just sort of a checklist because people were, do you have access control list? Yes, we do. Do they work? Well, you're not supposed to ask that question. All right, well, from there, there's no end to this set of things you can do with this capability. And so in the mid-2000s, DARPA started taking an interest in some of these open source operating system things. It's like, gee, maybe the day is coming when we're not going to just be buying our operating system from the vendors of the hardware. Maybe we're going to start running this Linux thing or this BSD thing or whatever. And we sort of need to have those things do the things that we need done. And so they funded a lot of work to add these things like mandatory access controls to some of the open source like Linux and BSD. A lot of times people don't quite understand things like the difference between like ACLs versus mandatory access controls. The ACLs is something where the owner of the object gets to make the decision about what gets done to it. Whereas mandatory access controls are imposed system-wide. So the system administrator makes decisions about the way certain things are going to be done, and then the users just have to live with that. So it's sort of a different layer in the hierarchy of where these things are done. So the idea then is that the mandatory access control framework is far more than just access to files, which is what I'm pointing to here. Because it allows you to essentially hang this sort of information on executables, on file descriptors, on sockets, or any random file, and then impose these sort of system-wide controls. So in the military case, of course, they care about if something is secret, then it can't flow down to something that's confidential. It could flow up to something that was top secret, but once it got up there, it couldn't come back down. These are things that the typical commercial user doesn't care about, but the commercial users do tend to care about their data integrity. So the bank doesn't really care if someone else can sort of see what your balance is at an ATM, but they sure don't want you to walk up to the ATM and be able to take money out without being charged against your account. And so these mandatory access control frameworks allow a great deal of flexibility in the kind of modules that you build and the kind of way that you enforce these things. And from the file system perspective, again, these are things that just get stored in the access control list or in the extended attributes. Okay, the key bullet point here at the bottom is that the file system is not codifying how the labels are used or enforced. It's just storing them and enforcing who's allowed to change them based on the headers in the records and producing them when appropriate for making permission checks. All of the policy about how they're used is in the Mac framework, which I'm not describing in this slide. Symmetric multiprocessing. You may remember the days when you only had one core. It wasn't all that long ago, actually, but they sort of ran out of steam on making single cores go faster, so they just started making more of them. And of course, when you have multi-threading, it becomes far more complex, whether it's the application or the kernel. At any rate, we had what was very much a single processor operating system, and we needed to get it to work in a symmetric multiprocessing way. So it's the usual. You start with a giant lock around the kernel, so only one thing can be going on in the kernel at a time. That gets you up to n equals 2 processors, one that does user stuff, one that does the kernel, because the kernel is usually about half the time. And but it doesn't scale past that. So you've got to go then down piece by piece and take out the giant lock and replace it with finer grain locking. And from the file system perspective, the first part that we did was the vnode interface, which divided between the file systems. It doesn't do you any good to do the file systems if the disk subsystems aren't fixed. So the next piece was the disk subsystems, and then finally the various file systems. And so in 2004, the vnodes, 2005 was the disk subsystem, and 2006 was the fast file system itself. And today, it's kind of interesting. You want to make their locks no finer grain than you need to, because locking just takes time and it's overhead. And so the less of it you do, the happier you'll be in terms of performance. But you end up then getting locks that get too hot. There's too much contention for them, so you need to figure out how to split them apart. So it's not like this is a problem that you solve once, because the number of processors just keeps growing and growing. So this was sort of the first pass at it, and this worked very well for n equals 4 and pretty well for n equals 8 and not very well above that. And so there's been at least 3 new generations of locking that have gotten put in so that we can now run up to around 64 really well. And once you get past there, there's still some issues. But that's really more memory hierarchy issues than it is the locking issues. So then you think, like you do something in 1982 and you're done with it, right? But no, there's always more. So we had soft updates, and they worked, but then we had to, reclaim space, as I mentioned, with background FSCK. And background FSCK works, but it takes a couple hours, and while it's running, it's pounding on the I/O subsystem, and so other things slow down. And people don't like that when it goes on for hours and hours and hours. And so someone at one of these conferences, I believe it was, came up to me and said, you've got soft updates. There's really only like a couple things that are not being consistent. Why don't you just add a journal just for those things? Because that's going to be, how hard can it be? I hate anything that starts with how hard can it be. The answer is that it doubled the size of the file system implementation, and it doubled the number of things that soft updates needed to track. But conceptually, it works pretty well. We're only going to journal the operations that orphan resources. It turns out that the journal only needs to be 16 megabytes, and that's independent of the file system size, because really the number of transactions that get committed before you, or that get into there before you're essentially forced to finish them because you're running out of space to store all the soft update dependencies. In fact, when we wanted to test to make sure that the code that dealt with running out of journal space was working, we couldn't come up with anything that would use up to 16 megabytes. And so we cut it down to 8, and then to 4, and then to 2, and then to 1. And finally, when we got it down to about 3/4 of a megabyte, we could finally reliably run out the journal and make sure that it didn't keel over. But we still make it 16 megabytes just on general principles. So what do you actually need to journal? Well, the free operation in the maps that are tracking the blocks and inodes, because that's the thing that's getting lost. Now, in order to be able to track the inodes, you've got to be able to track link count changes, because it's when link count goes to 0 that the thing is going to be freed. And so if you're in the midst of having that happen, you need to know that that's happening, because that's what's going to ultimately drive it to being freed up. And then one other just nasty fly in the ointment is the unlink while referenced file. Unix has this interesting semantic that you can open a file and then unlink it, so it has no name left, but as long as there's a descriptor that references it, the file has to be there. And you'd say, well, that's crazy. Who does that? Well, it turns out that lots of daemons do that. They have something where they just sort of need a scratch file, and they don't want to have to clean it up at shutdown in case the system crashes, so they just open it and unlink it, and then they may just have that thing open and not be like reading or writing it for days at a time. So you can't just sort of look at it and say, well, that's 3 days since it's last been looked at. It's probably safe to remove. Nope, it's not the case. And so you've got to track these things, and it turns out that that's just a colossal pain in the neck. You end up having to essentially have a linked list through inodes on the disk, which is, it turns out to be a great assignment. One of the assignments that I gave to some of my students at one point was, write the code that keeps a consistent linked list on blocks on a disk with a head pointer in the super block, and so that it's like always consistent, et cetera. It's non-trivial exercise. At any rate, this is also where I came to understand the aging process and software development, let me put it politely. I actually had a student come to me when I was about 35 and say, so now that you're too old to code anymore, what do you do? Well, I took some comeuppance with this, but the fact of the matter was that at that point I was running the CSRG, and I was really being much more in management than I was in getting any code written. But by the time we sort of wrapped that up, and there was this little lawsuit which also kept me tied up for a while. But once that all got resolved, I finally in my early 40s had an opportunity to do some more coding, and worked fine, no problem. In fact, that was when I was doing the original soft updates, which was probably the most complicated piece of code I'd written at that point. And it was great. It worked. Everything was happy. And some more time passed. I wrote a book and did some other things for a while. And then into my 50s, and it's time to do this journaled soft update stuff. And I start looking at it, and I'm looking at the amount of code that's involved, and think, oh man, this is just going to take forever. But then I found this 28-year-old that was, he had understood how soft updates work, one of probably 3 people in the world at the time. And I said, well, would you like to help me with this? And I have like some data structures and stuff written, and he takes that and starts pounding away on it. And the next, we're pretty far away on time zone, so we're sort of awake at different times. So I would wake up in the morning, and in my mailbox would be like 1,000 lines of code. And like, oh my God, and it'd take me like all day just to read it and comment on it and say, well, this is good, and what about that? And maybe you should try this and this. And then I'd go to bed, and the next morning it'd be, well, your ideas here and here, they seem like they might be plausible. Those are utterly stupid. I don't know what made you think of that. And here's another 1,000 lines of code. Sort of some of it rewritten and some of it new. So anyway, the beauty of this was in like 4 months' time, we got the whole, 15,000 lines of code written. We, note the use of the term we here. So I highly recommend this when you get into the, when you can start to see gray hairs, this is a great technique for getting a lot of code written quickly. Yeah. not only that, but it actually works, and you have someone else to bounce ideas off of. Now I'm in my 60s, I have to make my next big decision, but I'm definitely going to stick with that part of it. All right, raising the block size yet again. So we finally turn the corner, and the disk manufacturers wake up to the fact that 512 might be kind of a silly sector size. And so they switch to 4K sectors. And in doing so, they instantly double the amount of capacity of their drives, because it turns out that you have runs of bad bits. And so whether you have a 512-byte sector or a 4K sector, the size of the amount of space you need for the error correcting is almost identical. And so you get rid of 7/8 of all the error correcting bits, and voila, you have more space available. Of course, they have to have backward compatibility, and if you're foolish enough to actually try and use 512 sectors on something that's natively 4K, you get new meaning to same-day service in terms of delivery of data from your disk. At any rate, we were not about to make that mistake, so we raised the block size to 32K with 4K fragments, driven by the technology change saying 4K was the smallest you wanted to allocate. So once again, small files now use a minimum of 1 disk sector, so we can say, and we get perfect layout, perfect packing onto the disk, and as usual, it sort of doubled the throughput. So it was winning. So the last thing that I want to bring up is this optimized metadata layout. This is actually based on some work that was done in the Fast FSCK paper of Fast 2 years ago. And it was one of those ones which Margot sort of alluded to, where they had to do thousands of lines to change to the ext file system. And I listened to the paper, and I think, that's a great idea. And instead of going to lunch, I just sat down, and in 90 minutes of lunchtime, I just wrote a policy routine that did exactly that. It's about 150 lines of code, and it does more or less what they did, although with a little more flexibility to it. The idea is you're going to hold the first 4% of each cylinder group to use for metadata. In their case, they had to absolutely reserve it, but in our case, it's just advisory. Everything's advisory. So we save 4%, but if we run out of it, we can put, we'll just put the metadata elsewhere, and if we run out of data space, we can use the metadata for data, et cetera. So it's just advisory, but we're going to hold around 4%. And then the inodes, of course, are at the beginning of there. And then this 4% area, which is where we're going to put metadata. So the directory block, the contents of directories and indirect blocks are going to go into that area. So all of the directory information, all of the indirect blocks are sitting right there, right at the beginning of the cylinder group, and collected together in one place. The one exception to that is the first indirect block gets put in line with the data, because you have 12 blocks and then the first indirect block. And so if you have to do a seek to go get that, it makes the sort of slightly bigger than small files not work very well. And there's quite a few of those. So that's the one exception where we found it was better to keep those out with the data. So the benefits of this technique is it certainly speeds file tree traversal, because all the directories are in one place. You don't have to move very far to get it. It speeds random access to a file, because all of the indirect blocks for that file are in one place. So once you've read one of them, the disk cache conveniently also sucks in all the rest of them for you typically. And so now, even though you're way off somewhere else getting the data, you need the next indirect block. It's like, oh, the disk already has that. And so you just pick it right out of there, and you don't have to go zooming back to pick it up. And the FSCK gets to run much faster. Not that any of you probably care about that, but FSCK needs to read the inodes, the directories, and the metadata blocks, and they're all right exactly where it needs them. So it makes FSCK run way faster, which was the point of their paper. So in this case, the metadata area is advisory. As I said, if it runs out, you can put metadata in the data area. If the data area runs out, you can use the metadata area. And it's handled on a per cylinder group basis. So you can run out of space on one cylinder group and have to overflow, but that doesn't mean you have to overflow in all the other cylinder groups. So the upshot of it is that like I said, it's 150 lines of code. It's just this policy about, when the file system comes and says, I need to put down a metadata block, where should I put it? You say, well, put it there instead of over there. You say you want it there, but the underlying policy or the implementation routines will avoid having you accidentally over-allocate. It'll say, oh no, that's actually in use here. I'll just sort of put it somewhere nearby. And so it just all kind of works, and you don't have to think too hard about it. So that is what I have to say, and I have just a few minutes for questions, which I believe you're supposed to ask at the microphone.
Hi. I counted maybe 2 or 3 slides about the problem of protecting metadata consistency. My impression is that both in the talk and in the history of file system development, less attention has been paid to the problem of protecting the integrity of user data in files. Is this a problem? It strikes me as sort of like the police department whose primary policy goal is preventing police officers from being mugged. It's a good goal, but it's not the only goal, right?
Yes, I mean, you make a very good point. We have to protect the police officer, so that we absolutely have to do that in the file system. The users, however, we provide a mechanism for them to get consistency, which is the fsync system call. So you do the fsync system call. That call does not return until all of your data is on stable store. And even things like...
It's an ordering primitive, not an atomicity primitive.
Well, yeah, I mean, it's guaranteeing the consistency of your data up to that point in time. So if you're like an editor and you want to make sure that the new file is there before you delete the old one, you would do an fsync. Or if you're a spooler, a mail spooler, and you want to, before you say, yes, I got the mail, you want to make sure that you actually have it. So it gives you that ability. Now, you can do logging style of file systems which are keeping all of the user's data, not just the metadata. But you still need something like fsync to ensure that the log has been written. So the user has to give you some hint. Unless you've got NVRAM available to you, you're just not going to always be exactly consistent right to the second. We guarantee that the metadata is because we have to be able to recover, and so we make sure the log is written or whatever. But to keep the user data absolutely consistent at all times, if we don't have something like NVRAM, it's just would be too slow.
Yeah, you mentioned file system consistency. One of the features of System 5 file system, which is what you replaced the fast file system, is that there was a single superblock. And the fast file system has multiple copies, and that was really a great thing because you had this one block, super block, and if that block was corrupted, you lost the whole file system. So how did that come about?
So the way it came about is because I lost too many file systems because I lost my super block, and I said, well, I'm done with that.
Right.
So I just dropped in. In order to make that work, the thing that would make that hard on the System 5 file system is that they had stuff that was changing all the time in the super block. Mm-hmm. So to make that work, we split sort of the knowledge of the super block into things that didn't change at all or very slowly, and things that changed quickly, like the bitmaps. And so we created cylinder group maps, which are the things that change quickly, and we didn't have redundant copies. And then the super block, since it didn't change other than when you changed like some policy parameters in it, we could just drop gazillions of copies around the disk, and we didn't have to worry about keeping them up to date because they were just up to date all the time. And so it wasn't, I don't think that the System 5 people didn't think about it, it's just that they couldn't easily do it.
Because
so
of the
we found a way of changing it so that we could.
Thanks, that helps.
Hey Kurt. One great stuff, obviously. What about checksums over user data and checksums over metadata? How do you see that fitting in, and when are we going to see that?
So checksums over user data or metadata is a great idea. It's much harder to do it in an overwriting file system than in a copy on write file system. So ZFS, of course, does that in spades. They have redundant copies of all the metadata, at least 2 copies, and you can ask for 3. It has the ability to ask for 2 copies of the user data. And because stuff isn't overwritten, you can calculate that checksum and write it out, and it's just there, and it's correct, and it's never changing. When you're overwriting a block, you don't want to store the checksum in the block because you don't get the integrity that you would like. You need to store it elsewhere, because that way if the block gets corrupted, the checksum will let you know that that happened, which might not happen if it was like, a different block got written to that location but had a correct checksum in it. So because the checksum has to be separate from the data block, anytime you have an overwriting file system, you have these periods where things are inconsistent because you've written one or the other, and it looks like it's wrong when it's not. It just isn't finished. So it's something that I had looked at, and I just struggled with how to make it work. And then, of course, when the non-overwriting file systems just did it, it's like, duh, that's the obvious way to do it. And that is most critical, or becomes more and more critical as the file systems get bigger. So when you have the just ginormous file systems, you really desperately want to have that. So it's one of those things where I've just decided that the technology of the fast file system is just not well suited to it. And if that's something where you need that, you should use the file system that does it well. So my recommendation to you is go to ZFS, if that's what you need.
It's interesting how you, Konstantin Shvachko, one disk. So it's interesting how you were explaining how the file system was losing the dependency on abstracting of the geometry of the hard drive, right? And I had sort of a science fiction question. What would be ideal geometry of a disk drive? I mean, 3-dimensional, 4-dimensional, I don't know, for file systems in general?
The best one is ones that are it's a hard question. I guess I would say something that's essentially a flash drive is best, because then access to all blocks is absolutely equal. And I can't imagine any number of dimensionality of a physical drive that would give you that. But we've pretty much gotten to the point where what's important to us is that we need a way of knowing whatever the underlying technology is, what's it going to do well. And sequential layout seems to be the answer to that. And so, in essence, we've sort of adapted to what the current technology is. Until you start to get to something like a flash drive, I can't really think that I would want much different out of the drives today. So last question.
Thanks, Kirk. So this is a great overview of all this history, a few small pieces of which I actually saw. What's in the future? Are there things that you wish the file system were doing that you want to get it to do? Are there changes due to technology, the new flash drives or shingled magnetic things that you think will drive new changes? What will you be telling us in 10 years here?
Well, actually, that's a talk that I'm going to give in 2 days' time. Turns out that Netflix makes very heavy use of the fast file system for their servers. Which, in case you didn't know, serves up 1/3 of all the bytes that flow across the internet. So they've asked me to talk about, where those things are going. The answer to that is ask me later, because these folks want to get some coffee, I'm sure. All right, thank you very much. And